Welcome back. This will be a video lecture on section 2.3, spanning sets and linear independence. There are basically two topics in section 2.3, spanning sets of vectors and linear independence. I will cover each of these topics in a separate video lecture. So in part A, we will talk about spanning sets of vectors. Now let S be a collection of vectors in n-dimensional space. We'll call them V1 through Vk. And let B be another vector in n-dimensional space. We will say that the vector B is spanned by the set of vectors S if it can be expressed as a linear combination of these vectors. Now in this picture, I've got a vector B being expressed as a linear combination of some vectors U and V. So U is pictured here in red, V is pictured in green, and B is pictured in blue. And we can see that by stretching U by a factor of 2 and then adding on 3 times the vector V, we can build a bridge from the origin to the tip of B. And this is the language of spanning, right? We're in a sense building a bridge using the vectors U and V to get us from the origin to the tip of B. And so that's the language of spanning. It's equivalent to saying that the vector B is a linear combination of U and V. Let's look at the following definition. If S is a collection of vectors in n-dimensional space, and we'll call those vectors V1 through Vk, then the set of all linear combinations of those vectors is called the span of that collection of vectors and is denoted by the word span wrapped around the collection of vectors. Now, it is typical to represent that entire collection of vectors by a single symbol S in this case, and so we can just call that the span of S, where S is standing in for that entire collection of vectors. So that's going to be our shorthand. Span of S will be the set of all vectors that we can reach from this collection V1 through Vk by taking linear combinations of them. All right, if the span of S is all of n-dimensional space, then S is called a spanning set for n-dimensional space. Now, in order to get comfortable with this concept, let's work a couple of problems. So in our first problem, we're asking, is this given vector in the span of this collection of vectors? Let's head over to the document camera and look at the solution to this problem. Welcome to the document camera. The problem that's before us is this. We've been given a pair of vectors U and V, and we've been given a third vector, B, and the basic question is, can I write B as a linear combination of U and V? Is B in the span of that collection U and V? Now that means, can I find some constants P and Q so that P times U plus Q times V gives me B? Now, we've seen this before, but it never hurts to see it again. I want to show you how we can first think of this as a system of equations and then put it into an augmented matrix that we can easily interpret. So let's take a look at the corresponding system. By comparing first components on both sides of this equation, we can see that P plus 3Q equals -1, 2P plus 8Q equals -6, and negative P plus a negative 5Q, or negative P minus 5Q equals 5. So this has a corresponding system of equations associated with it. And when we lift this system and place it into an augmented matrix, what we discover is that we could literally go from the spanning question to this augmented matrix by simply taking our vectors U and V and making them the columns of our coefficient matrix, and then taking our vector B, which is being tested, and making it this constant vector on the right-hand side of our augmented system. So it turns out we can go immediately from our spanning question to our augmented matrix by simply taking these vectors and making them columns. These two vectors form the coefficient matrix, and the vector to be tested forms the column of constants. Okay, now all we have to do is row reduce this, get this down into reduced row echelon form, and we can interpret the consistency of this system. Does it have a solution or not? Now, I did all that work ahead of time. We've done a lot of that already, so you don't need to see all the gory details. But I did a sequence of elementary row operations. And this was reducible to 1, 0, 0, 1, 0, 0, 5, negative 2. And this is the important entry now. It turned out to be 0. And that's good news because this is a consistent system of equations. That is not an inconsistency, and we can easily interpret this answer. There's a p and a q variable governing these columns, and so this says that p is equal to 5 and q is equal to negative 2. Now we can go back to our original formulation of this problem, and we can see that 5 times this vector plus a negative 2 times this vector gets me to the vector b. And so the question, is b in the span of uv? And the answer is, because of this, affirmative, yes. Okay, so that's how we will typically answer a spanning question like this. We'll think of the question, we'll formulate the question, if only in our minds in this fashion, but we can quickly go from this to the corresponding augmented matrix, do the row reduction, and check to see whether the system is consistent or not. If it's consistent, we can find a solution to the spanning problem. If the system is inconsistent, then this vector is apparently not spanned by these columns. Okay, let's head back to the class notes. Let's take a look at another problem of the same type. Is this vector with components 5, 1, 5 in the span of this collection of vectors? Let's go to the document camera and work out the solution to this problem. All right, welcome back to the document camera. The problem before us is to see whether this vector b is in the span of these vectors u and v. Can I find a linear combination of u and v that produce the vector b? Now, as in our previous problem, we can kind of cut to the chase. We can produce an augmented system by literally lifting these vectors out and making them into a coefficient matrix and a column of constants. So let's go ahead and form that augmented system. And now we've done a lot of this kind of work, so I'll just cut to the chase. Our next step is to check the consistency of this system, and we're going to do a sequence of elementary row operations and put it into reduced row echelon form. So there's going to be a sequence of elementary row operations, which I've done already, and the question is, what is this reduced to? Well, in this case, the reduced row echelon form looks like this. And you can see that this is a catastrophe here, right? This is an inconsistency here. Our variables are p and q, and this last equation is telling us that 0p plus 0q is equal to 1, which is a contradiction. So this system, and therefore this system is inconsistent. And that means that the answer to this question is no. There is no way to combine these two vectors to give us this third vector. So the answer to the question, is b in the span of u and v, is simply no. The corresponding system of equations is inconsistent. Okay, let's head back to the class notes. Now we can summarize the work from our last two problems as follows. So let S be a collection of vectors, let's say v1 through vk. Let those be vectors in n-dimensional space. And let b be another vector in n-dimensional space. Now the question we've been asking is this: is b in the span of S? In other words, is b a linear combination of the vectors v1 through vk? Now, what the work in our last two problems has shown us is that we can answer the question by doing the following things. We can take the vectors v1 through vk and make them the columns of a matrix, let's call it A. The vector is in the span of S if and only if the system of equations with this augmented matrix, A paired up with the column B, is consistent. In other words, once we've produced this system, we can check to see whether it's consistent or not by looking at its reduced row echelon form. If that is a consistent system, then B is in the span of S. And if this is an inconsistent system, then B is not in the span of S. And so this gives us an all-purpose method for testing the question, is B in the span of S? It's equivalent to asking, is this system consistent or not? Let's look at theorem 2.4. A system of linear equations with augmented matrix A, B is consistent if and only if B is a linear combination of the columns of A. Now, in the last few problems, we have been essentially studying this theorem, at least in this direction, in this reverse direction. We've been looking at the following problem. Is a vector B in the spanning set of some vectors whose columns form this matrix A? And what we've realized is that that's equivalent to looking at this augmented matrix, studying its reduced row echelon form, and determining whether this system is consistent. If the system's consistent, then B is in the span of A, and if this system is inconsistent, then B is not in the span of A, or B cannot be spanned by the columns of A. Now let's think about the meaning of theorem 2.4 in this direction of implication. What this theorem is inviting us to do is to look at any system of equations and think of it as a spanning problem. Let me show you in the context of a particular system of equations. So let's imagine that this system of equations, at least in this augmented matrix form, has come to us from some context. Let's call the unknowns, let's call the vector of unknowns, let's say A for this column, B for this column, and C for this column. So we're trying to solve this system of equations in the unknowns A, B, and C. Well, we know we can perform a sequence of elementary row operations, and that will tell us a lot about the structure of the solution set. In this case, this system has this final reduced row echelon form. All right, let's see what that tells us. It tells us that the unknown A is equal to 2, that B is equal to -1, and that C is equal to 3. Now what we can do is we can take those values, those solutions, and we can interpret them this way. I can take the value of A equal to 2 and use that as a coefficient that's multiplying our first vector. -1 will multiply our second vector, and our 3 will multiply our third vector. When you plug those in, this being a solution to the system means that this left-hand side will add up to this column of constants, this -171 vector here. In other words, we're showing through this solution that the vector -171 can be expressed as a linear combination of the columns of this matrix A. So what this theorem is inviting us to do is it's saying anytime you see a system of linear equations, independent of the context, irrespective of where that system came from, once it's in this augmented matrix form, we can always think of it as the following question: is this vector in the spanning set of these columns? It's really the same problem. Okay, so that's really what theorem 2.4 is telling us. It's saying that all such systems of equations in the end can be interpreted as spanning questions. Now I want to close this subsection, spanning sets of vectors, by looking at 3 additional problems. So let's take a look at this first problem. Let S be this collection of vectors. So here are 2 vectors in 3-dimensional space. Now we want to find conditions on A, B, and C so that the vector with components A, B, C is in the span of S. So let's head over to the document camera and look at the solution to this problem. All right, welcome back to the document camera. In this problem, we have to find conditions on these components A, B, and C that will guarantee that the corresponding vector is in the span of these vectors, in this case 1, 2, -1, and 3, 8, -5. Now what that means is that when we form the appropriate augmented system, in this case 1, 2, -1, 3, 8, -5, A, B, C, this question is solved by showing conditions on A, B, and C that always produce a consistent system. So we have to know, what are the conditions on A, B, and C that make this system consistent? All right, so that's the question. right? Now we're going to find that this is going to force some conditions on A, B, and C. They can't just be anything. For certain choices of A, B, and C, this system will be consistent. And for other choices of A, B, and C, this system will be inconsistent. And our task before us is to dig out the conditions on A, B, and C that will always produce a consistent system. Now, how do we do that? Well, we just have to do elementary row operations until we get this into its reduced row echelon form. Now, let's go ahead and work with this leading 1 to eliminate the 2 and the negative 1 that sit below it. So I'm going to do a negative 2 times row 1. And I'm going to add that on to row 2. And I'm going to do 1 times row 1. And I'm going to add that on to row 3. Now row 1 is not changing, so I'll just put that one in right away. Now let's see the effect on row 2. Remember, I'm multiplying by negative 2 and then adding down. So that's going to produce a 0 in that position. Negative 2 times 3 is negative 6. Added onto the 8 gives me a 2. Now here's where it gets tough because I have to work with these symbols. And so I have to do negative 2 times A and add that onto B. So that's going to be B minus 2A. Okay, and here I'm going to do the row operation. I'm going to use row 1 to affect row 3. And I'm simply multiplying by 1 and adding, so I can just add down. So 1 and negative 1 are 0. The 3 added onto the negative 5 is negative 2. And then the A added onto the C is simply C plus A. Okay, now you can probably sense that this column is going to get more complicated as we continue to do our steps, and you're absolutely right. Now, our next step is to turn this into a 1 by scaling row 2 by a factor of 1/2. So we're going to scale by 1/2. Now this only has an effect on row 2, so I'll just rewrite 1, 3A, 0, 1. Now I'm scaling by 1/2, so it's going to be 1/2 of B minus A. And I'm leaving row 3 unchanged. All right, great. Now, my next step is going to be to use this leading 1 that I've created to eliminate all of the other non-zero elements in its column. So I'm going to have to do a couple of row steps here. Let's continue here. I'm going to have to take negative 3 times row 2 and add that onto row 1. I'm going to have to take 2 times row 2 and add it onto row 3. So row 2 is going to be used to affect changes in rows 1 and 3 according to this recipe. And let's take a look at the effect. I'm going to give myself lots of room on this side to incorporate the changes that we're going to see. Now remember, row 2 is not changing, so I'll have a 0, a 1, a 1/2 B minus A. Great. Now let's see the effect in row 1. I'm multiplying by negative 3 and adding up. So negative 3 times 0 is 0. Add up, that's still 1. When I multiply by negative 3 and add up, I'm going to get a 0 in that position. And that was what motivated this choice. Now we have some work to do. I have to take negative 3 times this entry and add it on to A. So let's just go off and do a little side calculation here. I'm taking negative 3 times this. And I'm adding it on to what's the entry that's in row 1 right now. So that's going to be plus 1, or 1 times A. So negative 3/2 B plus 3A plus A. And so that's going to be what? 4A minus 3/2 B. Okay, that's what's sitting there. Okay, we're done with that row. Now we're going to do the changes to row 3 according to this recipe. So we're simply multiplying by 2 and adding down. So no change there. That becomes 2 added onto the -2. That's 0. And now we have to do a calculation again like what we've just done. We have to take 2 times this entry and add it onto this entry. So again, that's another side calculation here. We need to take, let's remind ourselves, 2 times row 2. So 2 times 1/2 b minus a. And that has to be added on to what's currently in row 3, which is c plus a. All right, what's that equal to? Well, we can see part of the calculation is going to be b minus 2a plus c plus a. And so it's simply going to be b plus c minus a. Okay. Now remember, the question was, when is this vector with components a, b, and c going to be a linear combination of these two vectors? By putting it into this augmented matrix, that is the same as saying, when is the corresponding system consistent? And we can see that the test for consistency is going to be, when I look at this reduced row echelon form, this row of zeros on the left has to be paired up with a 0 on the right. Anything other than 0 in this position is going to produce an inconsistency. So when is this system consistent? When b plus c minus a equals 0. So that's going to be our magic condition on the vector ABC. It's going to be in the span of those two vectors precisely when b plus c minus a is equal to 0. All right, so I hope that illuminated something for you. Let's look at this problem together. So let S be this collection of two vectors in R2. The question before us is this: is the span of S all of R2? In other words, can I use these two vectors? Can I combine these two vectors to produce any vector in R2? Let's head over to the document camera and look at the solution to this problem. All right, welcome back to the document camera. The problem was posed to us in the following way. It says, is the span of these two vectors, 2, 1, and 5, 3, is it all of R2? Can I span the entirety of the plane just using these two vectors? Now, one way of thinking about that is that if we're just given a generic vector in R2, let's say with components A and B, is there a choice of P and Q that will get me to that vector? Can I take these multiples, these scalings of the vectors 2, 1, and 5, 3? Can I choose a P and Q that will get me to this vector AB? Now we know from our work that we can simply form an augmented system and check to see if it's consistent. If this system is consistent for all choices of A and B, if this is always consistent, then that means that there's always a way to find P and Q to solve this problem, and we can span all of R2. But if there are some choices of A and B for which this is inconsistent, then it can't be done. Okay, so let's go through the steps. We have to do, as in the previous problem, we just have to do a sequence of row operations to put this into reduced row echelon form. Now, I'm going to do this. This isn't technically a necessary step, but I like having a leading 1 to work with in my first position here. And I've already got a 1 here, so I'm going to do a row switch just to get the 1 in this position. I could scale by a half, but that's going to introduce these fractions into the problem, and I'd rather just not do that. So I'm going to do a row switch. I'll put the 1, 3, and B in the first row, and the 2, the 5, and the A in the second row. Now, I'm going to do 2 times this first row, negative 2 times this first row, added on to the second row. Now, what effect is that going to have? Well, I'm multiplying by -2 and adding down, so that's going to, well, row 1. Let me get row 1 fixed first. I'm getting ahead of myself. I'm going to do -2 times row 1 and add it down, so that's going to be a 0 in that position. When I take -1 times row 1 and add it down, that's -6 added onto the 5, that's -1. I'm going to take -2 times this, that's -2b, add that onto the current a, so that's a minus 2b. Okay, now we need to turn this into a 1, so I'm going to scale by -1. And now my last step is going to be to use this 1 to eliminate that 3. So we'll do a -3 times row 2 added on to row 1. Okay, and now we know row 2 is not changing, so we'll have 0, 1, 2b minus a. When I multiply by -3 and add up, that's going to stay as a 1. That's going to become a 0. And now we have to do a little side calculation. We have to take -3 times this entry and add it onto that entry. -3 times 2b minus a added on to the existing b. That's going to be minus 6b plus 3a plus b. So that's -5b plus 3a, or 3a minus 5b. Okay, and so the question is this system consistent? Absolutely. We have no inconsistencies here, and in fact, we can see exactly what to do. Let's remind ourselves, this is the column for the vector, or for the variable p, and this is the column for q. And what this is telling me is that if you hand me an a and a b, I can set p equal to 3a minus 5b, and I can set q equal to 2b minus a. So I can take your components a and b, run them through these formulas, and I can tell you exactly how much to scale this vector and exactly how much to scale this vector to produce this vector. And so the answer is, given any vector in R2, can I find a P and Q? Yes. I can span all of R2 using these two direction vectors, 2, 1, and 5, 3. All right, let's head back to the class notes. And finally, let's look at this last problem. Let S be this collection of vectors in R3. So it's two vectors in three-dimensional space. The question before us is this: is the span of S all of R3? In other words, can I combine, just using these two vectors, can I combine these vectors to get to any vector in three-dimensional space? So join me at the document camera for the solution to this problem. All right, welcome back. This will be our last problem for this first part of this lecture. So I made it a good one. Let's take a look at the solution. We want to know, this is very similar to the previous problem. I've given you two vectors in R3, and I'm asking you, can I use those two vectors in R3 and span the entirety of R3? Do these two vectors span R3? Now, one way to think about that is if I hand you an arbitrary vector in R3, so just think of A, B, and C as some arbitrary components, can I always manufacture a P and a Q so that P times this vector and Q times this vector will produce that vector ABC? All right, so we know that this question can be solved by looking at the corresponding system of equations or the corresponding augmented matrix. So we're going to cut to the chase. We're going to feed these vectors in as columns of this augmented matrix. And the question boils down to is, can I always solve this system? Is this system always consistent? Is it always consistent? If it's consistent, that means there's a P and a Q. And if it's inconsistent, that means there's no P and Q that will solve the system. Now, we know what to do. This is going to involve doing some elementary row operations, and we need to boil this down into its reduced row echelon form to check for consistency. Okay, so I need to take -1 times row 1 and add that onto row 2, and a -2 times row 1 and add that onto row 3. Okay, so what's going to happen is row 1 is not going to change. -1 times 1 is 1, so 1 plus 1 is 1 plus -1 is 0. I'll have a -1 added onto the 2. That's going to give me a 1. Minus a added onto the b will be b minus a. Okay, now we'll continue working on row 3. I'm multiplying by -2, so -2 onto the 2 is 0. -2 onto the 4 gives me a 2. -2a added onto the c is going to be c minus 2a. Okay, now I've created a new leading entry here, and it's already a 1, so that's nice. I'm going to use this 1 to eliminate the other elements in its column. So let's see, that's going to require a -1 times row 2 added onto row 1, and a -2 times row 2 added onto row 3. I'm going to give myself, as this column continues to expand. All right, let's take a look at row 1 first. What's the effect going to be? I'm multiplying by -1 and adding up, so that's not going to change. So when I multiply by -1 and add up, that's still going to stay as a 1. This will become a 0. Now remember, I have to multiply by -1 and add that on to a. So a -1 times the b minus a added on to the existing a. That's -b plus 2a. All right, let's see the effect in row 3 now. We're going to take a -2 times row 2 and add down. So that's going to stay as a 0. I'm multiplying by -2 and adding down. That's going to become a 0. And I'm multiplying by -2 and adding down onto this. So I'm going to have to calculate -2 times b minus a added onto c minus 2a. Okay, now what does that give us? A -2b plus 2a plus c. So that's going to give us the condition c minus 2b, or the entry c minus 2b. So we can see what our test for consistency is going to be. Is this always consistent? Well, that depends on what's sitting over here. Everything hinges on this element here. If c minus 2b is equal to 0, this will just be a row of zeros, and there will be no inconsistency. If c minus 2b is something different from 0, then this will be inconsistent. So our system will be consistent if and only if c minus 2b is equal to 0, or equivalently, c is equal to twice b. Now, I feel like that's not quite answering the question, right? Let's make sure we understand what's going on here. Can I produce a vector that's not in the span of these two vectors? Can I produce a vector that's not in the span of these two vectors? And the answer is yes, as long as I can produce a vector that doesn't meet this condition. Like if it meets this condition, it apparently is in the span. But if it doesn't meet this condition, then it's not in the span. So let's see if we can produce one. I can be somewhat cavalier with my first couple of entries. There's nothing on A whatsoever, so I'm just going to choose A equals 5. And maybe I'll choose B equals 2. And now I have to be careful. Whatever I put in here determines whether this is going to be in the span of those two vectors or not. So the one choice that I shouldn't make is 4. If I make b equal to 2 and I set c equal to 4, this will be in the span of those two vectors. So anything other than 4 here will be fine. So I'm just going to choose 3. All right? So 5, 2, 3 is a vector in R3, and 5, 2, 3 is not an element of the span of 1, 1, 2 and 1, 2, 4. Okay? That vector is certainly not spanned by these two. It is not meeting our test. All right, C equals 2b. 5, 2, 4 is in the span. 5, 2, 3 is not in the span. Okay, now this is kind of bumping up against an interesting thought, right? We're going to be heading in this direction a little bit later in the course, but here's kind of what this is bumping up against, right? We've only got two vectors in R3. And in some sense, we believe that three-dimensional space is three-dimensional, that it requires 3 pieces of information, right? And here we're saying, I'm only going to let you use 2 pieces of information, a direction, a scaling of 1, 1, 2, and a scaling of 1, 2, 4. And so it's actually quite believable that given only 2 different directions to move in, and of course, obviously adding and scaling those direction vectors, it's not inconceivable that this cannot possibly produce all of three-dimensional space. In fact, what we're showing is that it's only going to span vectors for which c equals 2b. So I can quickly look at a vector and check to see how that third component is relating to that second component. I can tell you immediately whether or not it's in the span of these two vectors or not. But this is actually quite believable. With only 2 vectors in three-dimensional space, we don't really believe that we can span the entirety of R3. So this result is not surprising, but we've actually worked out a very clever formula that tells us when these vectors are spannable, so to speak, by 1, 1, 2 and 1, 2, 4. So this brings an end to our discussion of spanning sets of vectors. We will continue this discussion of section 2.3 when I take up part B of this section, and we look at the important topic of linear independence. So I hope to see you at that video lecture. Until then, take care. Bye-bye.